Welcome, everyone, and thanks for joining us for the sixth Agro Lunch and Learn webinar of 2025. This webinar series is made possible through the generous support of Eurofin's AgroScience Services, and we sincerely appreciate their continued sponsorship. My name is Solito Sumalong from Solasta, and I'll be your moderator today. Before we dive into our talk, I want to take a moment to talk about something that makes webinars like this possible, our agro community. If you're not already a member, I'd strongly encourage you to join. Membership is the best way to stay at the forefront of the field, expand your professional network, and directly support the groundbreaking science you see here. You can add agro to your American Chemical Society membership or join as an affiliate for just $16 a year. It's a fantastic way to invest in your own career and our scientific community. Simply visit agrodiv.org and click Become a Member. For a few quick updates, we have several important award nomination opportunities coming up for worthy scientists, and all the details, deadlines, and contacts are on the screen now. Mark your calendars for the next ACS Fall National Meeting in Chicago next August. Calls for symposia are due on November the 10th. Please reach out to Dina Barrett for any questions. Lastly, the Agro Division is committed to building future-ready resources and engaging our members. We do need your help to continue to grow and succeed. Please visit agrodiv.org to learn more and get involved. Just a quick note on our format today. Please use the Q&A tool to submit your questions, and we'll be sure to address them at the end of the presentation. And while you're listening, feel free to introduce yourselves in the chat. Let us know where you work and what you do. We'd love to hear from you. Now a quick word on ACS community standards. We want to ensure a safe, collegial, and positive environment for everyone. The full text is displayed on your screen, but the main takeaway is simple. Please keep all interactions professional and respectful. This is especially important for the chat and QA tools. Any behavior that is harassing, threatening, or discriminatory is unacceptable and will not be tolerated. Thanks in advance to our great audience for helping us create a great experience for all our participants. Now it's my pleasure to introduce our speakers. First, Dr. Oscar Ortiz Escribano. He's a senior radiochemist at Labcorp with over 19 years of experience in the synthesis of carbon-14 radio-labeled compounds that span agrochemicals, pharmaceuticals, and industrial chemicals. He obtained his PhD in organic chemistry from the University of Nottingham and his bachelor's in organic chemistry from the University of Valencia. Second, Robert Unsworth is a scientific manager at Labcorp with over 25 years of experience in the field of GLP regulatory fate and metabolism studies involving radio-labeled pesticide, pharmaceutical, and industrial compounds. Robert has expertise in the design and management of a wide range of environmental studies with soil, water, and plants. He's a member of the Royal Society of Chemistry and attained his bachelor's with honors from Anglia Polytechnic University. And with that, we'll hand it over to Rob.
So yeah, we'll be talking about radiolabeling and plant metabolism practice from design to delivery. So plant metabolism studies are performed to determine that following application of a plant protection product, PPP, any residues left in or on a crop presents minimal risk to the health of humans and animals. To achieve this, we need information on the levels and the identity of any residues remaining in or on a crop. And this information is used to assess dietary risk and set maximum residue levels, known as the MRLs for crops. This helps us to ensure our food is safe to eat. Studies must be conducted on a representative crop from each group for which the use of the PPP is proposed. Examples like cereals and root vegetables, leafy crops, fruits, pulses and oilseeds. So types of crop metabolism studies. It's important to assess the metabolism of an active substance within a crop in order to establish its transformation pathway and to identify and characterize the resulting metabolites and degradation products. So the knowledge and levels of these residues combined with data on their toxicity informs risk assessment and the MRLs are set. And there are two types of laboratory-based crop metabolism studies. We have the metabolism in crops, and refer to the OECD 501, and also the metabolism in rotational crops, which is the OECD 502. So radiolabeling in metabolism in crops. Radiolabeling of the active ingredient is essential to allow precise tracking of the parent compound and its breakdown products with the plant tissues. And the radiolabeling enables identification of metabolites of interest and determine which compounds should be monitored for consumer safety. Radiolabeled active ingredients are required to allow quantification of the total extractable and unextractable radiolabeled residues. And if multiple ring structures or significant side chains are present, then separate studies reflecting labeling of each ring or side chain are normally required if it's anticipated that cleavage between these moieties may occur. Hence, these studies use a radiolabeled version of the active ingredient applied directly or indirectly to the crop. I wish to hand you over to my colleague Oscar, who will talk about radiolabeling.
Thanks, Rob, and hello to everybody attending this webinar. Well, as you can see in the agenda, what I will cover today is a small introduction on the use of carbon-14 in environmental fate and metabolism studies. I'll follow that with some background about carbon-14. I will then talk about a few considerations to think about when designing the radiosynthesis of a molecule. And finally, a Labcorp for the radiosynthesis of a molecule. Right, so let's start with a question. Why is radioactivity used in environmental fate and metabolism studies? The reason is that tracking a chemical compound in a complex system like soil, water, plants, or animals is not an easy task. These systems are full of natural occurring substances, and trying to detect your target compound from this background noise can be incredibly challenging. And that's where radiolabeled compounds come in, because by incorporating a radioactive isotope into the molecular structure of the compound, we create a highly detectable marker. This allows us to follow the compound's journey, whether if it's being absorbed, broken down, or transformed. And because radiolabeled compounds offer exceptional sensitivity, not only can they be followed, but their transformations can also be quantified. And whilst not always a requirement for all regulatory studies, the use of radiolabeled compound is preferred by the regulatory agencies, as it greatly helps in the interpretation of results. This is a list of regulatory studies that require the use of radioactivity. Later in the webinar, my colleague Rob will provide you with a more in-depth explanation of metabolism in plants and rotational crops. So why use carbon-14 for radiolabeling? Although you could use many other isotopes like tritium, sulfur-35, or iodine-125, it is often said that carbon-14 is the regulatory isotope of choice. One of the reasons for this can be found in the radioactive decay of carbon-14. As you may know, carbon-14 is a natural but unstable isotope of carbon that undergoes radioactive decay, as shown there, into stable nitrogen-14. That process emits an electron or a beta particle, and it is that electron that can be quantified by beta counting and beta imaging. Now, for some terminology, the emission of the electron is more or less equal to a disintegration. Then one disintegration per second is called a becquerel, which is the international unit. 37,000 becquerels is equivalent to 1 millicurie, which is the old fashion unit. The radioactive concentration in a molecule is measured in radioactivity per unit mass, and that's known as specific activity, with usual units being megabecquerel per milligram or millicurie per millimole. The maximum theoretical specific activity for one carbon-14 is 62.4 millicuries per millimole. Other advantages using a carbon-14 It's a long half-life. It's more than 5,000 years, so there is no need for decay correction. The radio tracer is considered to be chemically equivalent to the 12C analog. The radiolabel compounds can be prepared using standard organic synthesis, and also standard PPE can be used for the preparation of carbon-14. There is no need for special shielding, so gloves, lab coats, and safety goggles are sufficient to protect the user. More importantly, it gives a robust knowledge of mass balance, binding, tissue distribution, elucidation of transformation pathway, and quantification without the need of references. So now that we know that we are radiolabeling with carbon-14, how do we incorporate a carbon-14 isotope inside the molecule? Spoiler alert, you cannot just take your material, place it into a nuclear reactor, bombard it with neutrons to get your radiolabel compound. This would take years to accomplish, and most probably the compound will completely disintegrate due to the very large energy that it will be used. In reality, carbon-14 is produced in nuclear reactors by bombardment of beryllium or aluminum nitride with neutrons. This process takes up to 3 years, and the radioactive carbon dioxide produced is then isolated as barium carbonate. And this makes barium carbonate the universal starting material from which all of the carbon-14's compounds are prepared. Barium carbonate can be reacted in a multitude of ways to generate a variety of what we call carbon-14 building blocks. There are 4 primary building blocks that they are generated from barium carbonate, and you can see there. They are cyanamide, cyanide, carbon dioxide, and acetylene. They can then be further converted into more complex molecules and ultimately into end-use molecules. It's important to mention that the further away we go from barium carbonate, the more time will be spent, the more expensive it will be, and the more radioactive waste will be generated. This example molecule shows that basically it could be possible to radiolabel any position in the compound using molecules derived from the 4 main building blocks I just mentioned. So, although, as I said, we could label virtually any position in the molecule, not all positions are suitable for environmental fate or metabolism studies. So where should we place the radiolabel? Ideally, you would place it in a position that is not expected to be easily removed or altered by metabolic processes. This is what we call a metabolically stable position. These positions are usually carbon in aromatic rings, like the ones you can see there, quaternary carbons, sterically hindered carbons, or core backbone carbons. On the other side, what is considered as a metabolically unstable position, as a rule of thumb, any carbon that is attached to oxygen, nitrogen, or sulfur has more chances to be metabolically unstable. In these examples here, the carbon-14 radiolabel will be lost very early in a metabolic transformation, meaning that less information can be extracted from the study. It is worth noting that choosing a labeling position also depends on the type of study to be carried out. For example, an environmental fate study will require the label to be placed in a metabolically stable position, but in a dermal penetration study, any type of labeling position can be used as degradation of the molecule is not expected to happen. So now that we have decided where to place the radiolabel, we need to consider when in the synthesis to place it, as this can have a big impact on time and cost. So let's imagine we want to generate 10 millicuries of the radiolabel molecule on the right, and we want the radiolabel to be on that specific phenyl ring. The synthesis is 5 steps from the molecule on the left, and we have found a way to introduce the radiolabel on step 1. Now, if the overall radiochemical yield is 5%, we will require 200 millicuries of benzaldehyde, the starting material, to complete the synthesis. Now, let's assume that we are able to incorporate the label on the last step of the 5-step synthesis. The overall radiochemical yield then jumps to 50%, resulting in only requiring 20 millicuries of radioactive benzaldehyde to synthesize the 10 millicuries of product. This obviously will have a big impact on both the delivery time and the price of the radiolabeled material. As a conclusion, we would always aim to incorporate the radiolabel as late as possible in the synthesis. One last consideration regarding the labeling position will be the availability of the starting material to be used. In the following example, we are using the same starting material, benzaldehyde, but is labeled in 2 different positions. On the top one, the label is in the phenyl ring, and on the bottom one, the label is placed on the carbonyl group. Both would give us the radiolabeled test item in 1 step and with the same yield. Now, the key difference now is that the synthesis of the ring-labeled benzaldehyde is much more complex than the synthesis of the carbonyl label. Starting from barium carbonate, this will have a big impact on cost and delivery time for the final compound. So we can see all these concepts now into one case study. So imagine we want to radiolabel cypermethrin, which is a well-known pesticide. We have identified 5 possible labeling positions, and we have devised a synthesis route. And the different labeling positions are incorporated in the color places you can see in the scheme. We can simplify the scheme as before, and then summarize the number of steps and yields for each label formed. And if we then tabulate everything, we can get some conclusions like the green label, for example, would be the cheapest and fastest to synthesize, as potassium cyanide is readily available, and the synthesis would be only 1 step. Unfortunately, this labeling position would be only ideal to use in studies without metabolic transformations, as in those studies, the labeling position derived from the potassium cyanide would be metabolically unstable and would be lost early in the study. On the other side of the spectrum, we have the blue label, which would be metabolically stable, but it has the lengthiest and most expensive synthesis. As a conclusion, basically there is no right or wrong when choosing a labeling position. It is a balancing act between the cost of the radiolabeled starting material, the metabolic stability, the length of the synthesis, overall yield, and the type of regulatory study to be performed. Right. I will walk you now through our usual process for our radiosynthesis in Labcorp. The first step is to generate a custom quotation for our client. This usually starts with a discussion between the client, the radiosynthesis team, and the metabolism team. In here, we exchange the synthesis scheme, either which has been given by the client to us, and if that's not available, we can then develop it from available literature. We discuss and confirm the labeling position to be used, and depending on the onward study, how many radiolabel forms are required. Finally, we agree on the amount of carbon-14 test item to be synthesized to cover all the range of studies planned. Once we have won the work, we perform a low specific activity radiosynthesis, or what we call a trace and run. That uses a small amount of radiolabeled material mixed with mostly non-radiolabeled material. This minimizes the use of expensive radiolabeled starting material, which can cost over £60,000 in some occasions. The tracer run establishes the synthesis method and the scale we will perform the actual radiosynthesis, and also allows us to develop purification and analytical methods and confirms the yield of the synthesis route. once we are happy with the, oh, didn't change this. Go back. Okay, once we are happy with the tracer run, we will move into the main radiosynthesis, which this time uses only high specific activity starting material. The main radiosynthesis then produces high specific activity test item that is suitable for use on onward studies. So with the compound in hand, we then there we go. With the compound in hand, we proceed with the QC analysis, and we generate a certificate of analysis, which includes the site of labeling, the specific activity value, which we measure by mass spectrometry, and is generally between 40 and 70 millicuries per millimole. We also state the chemical identity of the compound, which is confirmed by coelution with reference standard and also by MS, and the radiochemical purity, which is required to be greater than 97% for agrochemicals. Finally, when the product is packaged and then is made ready for regulatory studies, which is the next step. This was my last slide, and my colleague Rob will now take over the presentation and give you an insight on plant metabolism studies. Rob.
Okay, thank you, Oscar. I'll be following through this agenda to be talking about plant metabolism studies. So the guidelines tell us how to conduct the studies for plant metabolism studies. The guidelines we use are the OSD 501, metabolism in crops, the US EPA nature of residue plants and livestock. For Japan, it's the JMAF guidelines we follow, and finally, for the OSD 502, that's the metabolism in rotational crops. So plant metabolism studies are performed to assess the metabolism of the active substance in the crop, following application according to normal usage or good agricultural practice, known as the GAP, and assess the levels of parent substance and its metabolites in the raw agricultural commodities, known as the RAC. Establish the transformation pathway, characterize and identify the metabolites, and so this requires the radiolabel test substance, which my colleague Oscar was talking about previously. And if the transformation pathway is the same in crops from 3 plant groups, then the results will cover all plant groups. And these studies are often referred to as the nature of residues studies. So information required before starting a plant metabolism study: the nature of the test ion, its structure, how many radiolabel forms will be needed for that test ion. So the target crops as well, whether they're cereals, leafy vegetables, fruit vegetables, or seeds, and say also the raw agricultural commodities depend on the crop type. And also that crop type, is that going to be grown outdoors, indoors, or greenhouse cultivation? So the type of active ingredient that's going to be studied, examples like fungicide, insecticide, or herbicide. The time and the number of applications should depend on the type of active ingredient and that mode of action. And so, for example, fungicides usually require multiple applications, and say herbicides may be applied pre-emergence. And so the crops used in the plant metabolism studies will depend on the intended use of the active ingredient or test ion and its mode of action. Studies may be conducted in 1 or several crops. Many crops are best grown outdoors in a normal season, as the results will be more realistic. And the examples of cereals and carrots are good crops to be grown outdoors. Certain crops would normally be cultivated under glass, though, like tomatoes. And so many crops, rice for example, can be grown indoors under controlled conditions and to allow them to be cultivated out of season. And so, and the varieties should be commercial varieties. They're grown in pots or containers, in soil or compost, depending on the requirements of the plant. And for specific crops, e.g. cereals, And for pre-emergence applications, it is necessary to sow those seeds, whereas certain plants can be obtained as seedlings or small plants, for example, strawberries and tomatoes, and translocated into the pots. And say also plant density should be similar to that used commercially. And plant crops require, in some cases, trees or vines to be treated, which would be applicable to apples and grapes. So the correct conditions for healthy plant growth will obviously include water, sunlight, and temperature. And if outdoors, plants must be grown in the correct season. And most seeds sown in the spring, as seedlings may need protection from the frost. And if inside, require correct day length, temperature for growth stage. For example, wheat, you'll need that cool germination to start them off, and then finally warm, dry, and sunny for harvest. And so the plants may also need fertilizer and treatments for pest or disease. And any chemicals applied must be structurally different from the test item. And for example, tomatoes will also require regular feeding, and say potatoes should be treated to prevent diseases like blight during the course of the study. And importantly, environmental conditions must be recorded in the raw data. And so the application should be carried out according to the Good Agricultural Practice, or the GAP. And this will specify the type and concentration of the formulation, for example, whether it's SC, EC, or granular, type of application, seed treatment maybe, or spray, the application rate, number of applications, say timing of those applications, which could be pre-emergence, forage, or at flowering, the intervals between the applications, the pre-harvest interval or timing of the final application before harvest to ensure any residues remain below safe levels. And also, finally, the dilution factor if applied in water as a spray. So regarding the application, the test item or active ingredient is formulated for these nature of residue studies. And formulating the test item requires us to combine the radiolabel test item with blank formulation ingredients often supplied for the studies. And if the test item requires radiodilution, this must be carried out first, and the specific activity be at least 1.7 kBq per microgram or 45.9 nanocuries per microgram. And so this is required so that we can measure down to 0.01 mg per kg in plant samples. Usually a formulation trial is carried out to assess the effectiveness of the method and the homogeneity and stability. And once the test item has been formulated, the homogeneity and the purity must be checked prior to application. And so once formulated, the test item is applied within the time that it's been shown to be stable for. And here is an example of an application procedure. So if applied by spraying, the surrounding area must be protected. In this example, polythene sheeting is used for this procedure. A tent is also made using a frame to fit over the plants that are in the pots. And the plants are treated inside the tent, usually by cutting small slits inside into the polythene. And the polythene is removed after a predefined time after spraying. And the test item is sprayed evenly over the plants, in this example using a handheld aerosol spray gun. And the spray gun may be rinsed with a small volume of water to ensure all the formulation has been sprayed. And then finally, the spray equipment is washed with solvent and the radioactivity determined to calculate the amount applied and the application rate. And so for sampling, once treated, the raw agricultural commodities are sampled, and this is crop dependent. So please refer to the OECD 509, which has details on the raw agricultural commodities for crop types. So for example, cereals will have forage, hay, straw, grain, or seeds will have forage, hay, and straw, plus beans and seeds. And obviously for leafy vegetables or only leaves, fruit may have to be peel and flesh, for example, like melons and citrus. Root vegetables, for example, carrots, are washed with water to remove soil. And crops that have been sprayed may be washed with solvent, and non-edible roots may be required specifically for JMAF guidelines. And for some crops and studies, intermediate samples or leaves may be taken as analysed to help to elucidate the metabolism pathway within the study. So the rack samples are usually divided into at least 2 weighed subsamples. And one subsample is stored in case required for storage stability or extraction efficiency investigations later on. And the other subsample is analysed to determine the total radioactive residue, which is known as the TRR. Fresh weights must be recorded following any processing, haze dried first, washing and drying, for example, potatoes and lettuces, peeling, especially specific to oranges, destoning for olives, and separation of grain or beans, which is applicable to wheat and soybeans. So moving on to analysis. So to determine the total radioactive residue, the sample is homogenized and aliquots combusted. And certain crops are difficult to homogenize and are best processed frozen in dry ice. And some of the challenges, tomatoes are mostly water, so they can be very hard. And straw plant stems are tough. And also, in addition, the nature of potatoes are also hard when frozen. So taking sample type into account when deciding on the homogenizer. And samples are weighed again following homogenization. And so if dry ice is used in the process to ensure the test matrix is kept frozen, allow that CO2 to evaporate before reweighing, and if in doubt, better to weigh more often. So the determination of total radioactive residue in the sample provides with the value of a dpm per gram, and the radioactivity is then associated with the test ion and its metabolites. And using the specific activity of the test ion, dpm can be converted to micrograms, and this equates to either micrograms per gram or mg per kg or parts per million, known as ppm. And this concentration of radioactive residues in the rack sample, and if the TRR is equal to the trigger value of 0.01 mg per kg or below, then no further work is required. And if the concentration of the radioactive residues is more than the 0.01 mg per kg, the sample must be extracted. So in this example, we have some example data in table 1 showing you some TRR values. So your initial TRR value is equivalent to 100%, and 2 applications in this case were made, first before forage sampling and second after forage sampling. So the concentration in residues you can see is increased between forage and straw, and concentrations in straw can concentrate as the plant loses moisture close to harvesting. And concentrations in grain are often much lower as not sprayed, and obviously didn't develop until after second application. So the residues in the grain are due to translocation through the plant. So use documented extraction methods if available, otherwise methods will have to be developed within the study. Samples are extracted often with neutral solvent or solvent water mixtures. Citronitrile is usually a good first choice. These types are generally more polar than the test item. So check quantities extracted by liquid scintillation counting in individual extracts to follow extraction efficiency, and continue until less than 10% extracted, then air dry and combust the post-extraction solids, known as the PES. And the amount of radioactivity in the extracts plus the PES should equal that initial TRR value. So further on the analysis, if the extractable radioactivity is less than the trigger value of 0.01 mg per kg and 10% TRR, then no further work is required. And so we do have this table on the right-hand side, which is from the guidelines, in this case the OSC 501. And if the extractable radioactivity is greater than the 0.01 mg per kg and greater than 10%, then the sample must be further analysed. And for sample concentrations between the 0.01 and the 0.05 mg per kg, characterization may be sufficient. And so for samples greater than 0.05, identification of radioactive components using chromatography is required. Identification means exact structural determination, while characterization is more descriptive and can be referring to polar or organosoluble fractions. The trigger values only apply, though, if there are no toxicological concerns with those components. So if the non-extractable residues are greater than 0.05 mg per kg and greater than 10% TRR, then attempts should be made to release further radioactivity for characterization identification, which can be treatment with enzymes. Mild acid or base can hydrolyze conjugated metabolites. Surfactants may release physically encapsulated radioactivity, and reflux with strong acid or base may release radioactivity which is incorporated into amino acids or sugars. Alternatively, procedures to fractionate the cell wall components, the Lang-Bartz procedure, can be conducted. So moving on to some more example data here, we have in table 2, distribution of radioactive residues. So in this example, we've got neutral solvent extracted between 82-86% for straw samples, shown on the for radiolabel A across the B. Further 8% in acidic, mostly shown through characterization as organosoluble, and the pairs is less than 10% TRR. So neutral solvent extracted for the grain, 41-75% TRR, and this was further shown as 8% TRR in acidic, mostly water soluble. So differences here: Radiolabel A has a pairs that's equal to 50% TRR, so therefore required exhaustive extraction, which was shown to be released under mild basic conditions, which the table shows in the left in the final few rows. Whereas for radiolabel B, the pairs, even though it was greater than 10%, but the concentration was significantly low at 0.03 mg per kg, so no further characterization was performed on the pairs. So ultimately, the aim is to extract and release greater than 90% of the TRR, and the extractable radioactivity must be identified or characterized. If most of the residue has been conclusively identified, individual low-level components may not need to be identified. Both concentration and the percent TRR need to be considered. Metabolites present in more than one fraction need to be summed to determine their exact levels. And studies may be conducted with exaggerated application rates to assist with the metabolite identification. However, those trigger values must not be divided. And say neutral extractions and initial chromatographic profiles should be obtained within 3 months from sampling, if possible. So moving on to chromatographic analysis, methods may be available or again developed in-house. Extracts may be combined in proportion where appropriate. Extracts are concentrated if necessary for chromatographic analysis, and plant extracts can be difficult to concentrate, clean up, can then assist or help with that process. And partition or SPE can be used for that cleanup and can either then be HPLC or TLC with radio detection can be employed. So metabolite reference standards are chromatographed with those samples, which are known as co-chromatography for assignment of metabolites. And the identity of metabolites is then confirmed in a second system, which may be TLC if HPLC was the primary, or by LCMS. And if initial profiles are not obtained within 6 months of sampling, then storage stability analysis will be required within the study. So moving further on to example data. So on table 3, we have some identification of radioactive residues for straw. So neutral solvent extract here comprised of 77% parent in the neutral extracts. So a further 4% as parent was shown in the organosoluble extract, moving into the second column. So the total amount then is summed. So the test item in straw, 80% was shown as parent of the TRR. And then we have examples of metabolites 1 and 2, identified as 5 and 1% TRR respectively in the final sums. And then characterization shown was 2.6%, was small polar components, and then often referred to as low level distinct radioactivity. And following on, some typical chromatograms from the radio detector. So on the left-hand side, neutral showing solvent extract comprised of the parent at 77%, and the smaller metabolites at 4% in the organosoluble extract. And the metabolites 1 and 2 identified as 5 and 1% was the two summed between those components. And finally, 2.6% characterized the small polar metabolites, which are the very small peaks which can be seen in the neutral extracts, which are non-distinct radioactivity. So, moving on to the transformation pathway. It's important to radiolabel, as we've spoken before earlier on in the talk, the active ingredient, as this allows the tracking for all the major metabolites and degradation products as far down the transformation pathway as possible. So in this example, we have the main parent molecule shown in the middle of the transformation pathway, and how the pathway can then be drawn between the components that are identified within the study. So moving into reporting. So the report should include obviously the test item and blank formulation information, radiodilution and formulation methods, details of homogeneity and stability of the formulation, a description of the applications, its timing, determination of the application rate, plant variety, maintenance, weather details as appropriate. Then moving into the sampling and processing details and weight should be reported. Importantly, the results, the chromatograms and the transformation pathway. And then finally, in the report, a table of key dates, which should be for the sampling, extraction, and the chromatography analysis. So moving on to talking about metabolism in rotational crops. So metabolism in rotational crops are a different kind of plant metabolism study. They are designed to show if a follow-on rotational crop takes up residues from treated soil. The studies are conducted in large containers of soil. Bare soil is treated with formulated test item at the highest seasonal application rate and then aged as follows. So the blank plant back at the 30 days is to stimulate crop failure. We have a plant back that can be between 60 and 270 days. This is stimulating rotation after primary harvest, and then finally a plant back containers for 270 to up to a year, which is the full rotation. And they're obviously not applicable to crops that are not rotated. Examples, obviously, fruits and on vines and trees and stone fruits. So metabolism in rotational crops, if the soil applications are conducted at the same time, then some crops will be grown out of season. So they're usually grown indoors under controlled conditions. Alternatively, the applications can be staggered, and then all the crops are sown at the same time in season, and they can be grown outdoors. And so it is necessary to sow the seeds, obviously for the crops of like cereals, the leafy vegetables, which can be lettuce or spinach, root vegetables, they can be carrots or radishes. And below we have an example table when such crops can be sampled, which is showing a wheat, a leafy vegetable, and a root crop. So moving on to the analysis. So the samples are analysed in the same way as samples from the plant metabolism studies. Initially, they are homogenized and the concentration of the radioactive residue is determined. If the TRR is equal to the trigger value, 0.01 mg per kg and below, as we said, no further work is required. If the concentration of the radioactive residues is more than 0.01, samples must be extracted. Example, samples of 0.01 mg per kg extracted, extracts greater than the 0.01, chromatographed, and say pairs greater than 0.05 and 10% require exhaustive extraction. And in addition, on the rotational crop, proportions of the soil are also analysed at sowing and harvesting of those crops. So metabolism in rotational crops, typical results, concentration of radioactivity increases from forage to hay to straw as the plant takes up more from the soil residues. And this is shown in our table on the right-hand side there, table 4 for those crops. And concentration in the grain, typically lower as this develops later, as mentioned before, requires translocation within the crop. And concentration in lettuces often decrease as the plant increases in size, and that concentration residues are reduced. And so concentration in carrot root often do remain low, whereas concentration in carrot foliage is higher and often increases as the plant grows in the soil containers. So that moves us on to the final summary. So I hope this webinar provided a solid foundation for conducting plant metabolism studies with radiolabel compounds, and I hope you all have a better understanding of, say, the integrated approach to the carbon-14 radiolabeling. So the conceptual design from radiolabeling positions through to synthesis, and how to design crop studies, the application and sampling techniques, and plus the analytical strategies, and hopefully there to generate the robust data for crop studies. I'd like to thank you all for listening to our presentation.
Thanks, Rob. Thanks, Oscar, for your great contributions to our webinar series. We do have a few questions that came in. We prefer to have it in the Q&A tool, but a couple of them came in the webinar chat. First, a remark. Thanks, Oscar, for the synthetic scheme. That was very helpful for the audience. We had a remark about that. We had a couple of questions I can combine from the Q&A session, the Q&A tool. We had particularly in the range of costs for doing a C14 label. What are the main factors that go into the cost? Could it be disposal? Could it be all those measures that need to happen to take this material outside a lab? Can you walk us through some of those factors?
Yeah, basically the biggest cost in a radiosynthesis is the radiolabeled starting material. So that's why we try always to push it at the end of the synthesis to decrease the amount that we need. Because as I said, for example, the type of radiolabeled starting material has a big impact as well. For example, the example I have there, bromobenzene, if you need to purchase or make, let's say, 100 millicuries of the material, that could cost you $50,000. For the same amount of carbon dioxide, you will be basically spending probably no more than $5,000. Then obviously you need to add all the steps, our work, all the weeks that we need to work, and all the reagents, everything. So everything accumulates, but the main driver for price is the starting material.
A question rolled in about analytical strategy. In addition to C14 radiolabeled material, do you consider or actively use stable isotopically labeled test substances to aid in the complex process of metabolite identification?
From the regulatory point of view, they stipulate you do need to use the 14C radiolabel. So from a regulatory point of view and submitting a GLP study, then we will only consider the 14C, and we won't look at any other isotopes, because that gives you the benefit. With the 14C, you get that radiochromatogram, which is separate from your UV chromatogram, and your UV chromatogram is then used to aid with your analytical standards for co-chromatography, and then you've got a lot cleaner 14C radio detection trace. So the two things are then separate.
Okay, great. A question rolled in as well about final reporting for non-extractable residues analysis. Do you need to specifically differentiate the concentration of residues in the food items versus feed items for regulatory compliance?
For regulatory compliance, so we go into the non-extractable and then characterize that material. From whether it's going to be, it goes in the full risk assessment for that pesticide or fungicide and obviously depending on its usage from a crop point of view, I wouldn't see a difference in that.
Okay. For both of you, if a client supplies a radiolabeled test material with a lower than ideal specific activity, what steps do your teams typically take, both in synthesis and in analytical, to ensure the study can still meet the required detection limits?
Well, if the specific activity is already lower than needed, is not much you can do. Either you make more of the high specific activity material and add it to that low specific activity material. If not, basically you cannot add activity into it, because once you radiodilute, you are done.
Yeah.
So you need to be pretty sure about that's why we make always high specific activity. And that's what we produce. It is kept in the freezers, and then the metabolism people will take the necessary amount. Then they will radiodilute to their specification, but they will not radiodilute the whole amount. So they can do several studies that may require different levels of radiodilution. But as I said, once the material is radiodiluted, you cannot reconcentrate it, basically.
Yeah, when a client comes in with a request, and we do have a request for you to provide contact information for radiosynthesis requests. When those requests come in to your team, who should, from the client's standpoint, who should they bring to the table for a robust initial discussion?
Basically, if obviously we need the structure of the molecule, if they have a synthesis, the synthesis they use to produce the molecule, obviously most times they do it in kilogram scale, but we work in milligram scale. So if they can give us the smallest amount synthesis procedure that they have, we can follow that. If they cannot provide a synthetic pathway, we go into literature, and then we will provide a way of making it that will introduce, as I explained, the radiolabel at different points, or which radiolabel will be better for the studies. We advise which radiolabeling position will be best for depending on the study that is going to be done. Then Rob will basically contact the client again and tell them if they need one or several labeling positions to be done in case there are different studies. So it's basically there's a conversation just before we start doing anything. There is a lot of steps that we need to do,
right,
that we can discuss with the client, obviously.
Okay.
Obviously, we need to know what studies and the number of studies they need, the applications, so that we can then work out those quantities, which obviously then feed into how much radioactive material needs to be produced, and whether how stable that radioactive material is going to be. Because there's no point producing loads of radioactive material if the studies are going to take years or over lots of applications. They then need to consider whether they need to make smaller batches and produce it over time, or they could then look at repurification. But if the stability does go off quite significantly over a period of months or years, they may be better to consider to sort of produce it in smaller batches of material. So there's quite a lot of different approaches.
It depends. If your compound degrades really, really quickly, then it's best to do several batches, but that's rare. That happens. We usually do a big batch because it's a lot more economically efficient for the client to make a big batch. It gets used, and then obviously before every metabolism study, the radiochemical purity is checked. If it falls below certain standard, then we can repurify the compound, because we have made it, so we know how to repurify it and put it back onto greater than 97%. And because we are all in the same building, it's rather quick to be done, because they tell us this has gone off, when can you purify? And it usually takes maximum 2-3 weeks to purify, and then they can start the study immediately after.
Yeah, you've mentioned a lot of you mentioned a lot of factors that certainly have it have that show up in the costs. Can you tell us a little bit about some of the factors that go into timeline for your projects as well?
Timeline basically is how long the synthesis is. We aim to do 3, 4, 5 steps, but we've done synthesis that required 13 steps in the past, and that can take up to 6, 7 months. Because as I said, first we start with a tracer run to check that the reactions work. If they don't work, then we need to go into the literature, modify them, keep trying, and until we are not happy with that tracer run, we will not go into the radioactive high specific activity synthesis, because if it fails, then we need to go back to the beginning. So it's mainly a number of steps, that determines, and obviously how well the chemistry works, because some projects, all the reactions work like a treat. Some others, they are awful, and you need to work more on them.
For Rob, I'm sure the guidelines dictate this a lot, but does Labcorp always analyze the soil before sowing and after harvesting?
Yeah, but that is normally quite routine, and we have a lot of sponsors that have that want to have information because they want to know the levels of residues that are in there and whether they're declining in the soil, and particularly at final harvest, it's important to know those residue levels that are still in the soil. So it almost is, you, as well as doing the crops, and you've got the 3 crops that you're doing over those 3 different plant backs, you've then got soil analysis on all those soil plots as well, which can to give you that further information on residues that are in the crops. And obviously, if you're seeing a lot of residues remaining in the soil, there's obviously that potential there for uptake into the crops. And say also in rotational crops, you can have, with some test components, you get no uptake after the first, say, 30 days, and that 270. So again, if you're seeing low residues and you're not getting crops, then you don't need all that analysis. We've had rotational crops where studies that all the analysis is being conducted on one crop type, say, for example, cereals, because you haven't had the same up. So you can get quite different uptakes between crops on a rotational crop study.
Okay, great, gents. Well, I'm going to close off Q&A at this point since we're near the top of the hour. What I'm going to do is for providing contact information for radiosynthesis requests, we can certainly follow up with Kyle in his follow-up email to our attendees, and also we can use that forum also to answer any unanswered questions along the way. All right. So thank you again so much. Let me share my screen again. Yeah. Well, thank you, Rob and Oscar, for your excellent presentation, and to our tech host based out of New Hampshire, Kyle Sawyer, and to Eurofins AgroScience Services for their generous sponsorship. We'll be posting any answers, as I said, to any unanswered questions. So keep looking for a follow-up email that will also include a brief survey. So please mark your calendars. Our next webinar is on November 12, where we'll close the year in collaboration with the great History of Chemistry Division of the American Chemical Society on another exciting topic, the wild history and sustainable future of phosphorus. We certainly at the Agro Division want to do more in terms of plant nutrition. We'd love to hear your ideas for future topics, so please reach out to me for support, and also to get your idea into the 2026 slate. So thank you all for your participation today, and we hope to see you next month. Thank you, everybody.
Thank you.
Thank you.
Bye.